Hello, Miss Raccoon.
Hello, I'm sorry I'm late. I'm having trouble getting my computer booted up, but I'll be on in a second. I just wanted to let you know. Hi, Gavin, Brittany, and Tanya,
Hi,
Melissa.
how are you?
Oh, good. How about you guys?
Good.
Doing all right.
My computer is doing some crazy stuff, so I had to reboot it, and it takes forever when you do that, apparently.
Every time I do anything that's the McGraw-Hill, like any kind of book or anything that's McGraw-Hill, it like does something to my computer. I don't know why.
Ugh, how frustrating.
Yeah.
Mine was making continually dinging noises, which is not very nice.
Especially on a Sunday.
Yeah. My husband's like, what is that? What are you
You're like,
doing? Uh, all right. All right, I think I'm gonna have to sign off this one on my phone so that it doesn't get feedback. So I'll see you on the other one. All right, I think I'm on now. Okay.
yes.
Well, Alyssa, you have a new background I'm gonna have to copy, I guess.
You'd like to get the Pepe Sylvia background? I had to import that.
What is this?
Pepe Sylvia?
Yeah, I don't know. I'm not cool.
It's pretty much like the embodiment of conspiracy theorists.
It's also the embodiment of keeping track of everything that's going on in school ever.
Yeah, that's probably what it feels like, huh?
Following every thread down the line.
Ugh. All right. What can I do for you? Wait, are we recording? We should be. Make sure. Yeah, it's recording. Okay.
Well, because we still have ways to take today, could we go over maybe chapter 4 first? Or
Sure.
week 4, I mean?
Sure. What questions do you have? I don't have anything prepared. But if you have
It's
questions, I'm happy to answer them.
it's well, conceptually I feel like everything's pretty much there. I guess it's
Good.
just I'm unsure how it's going to be asked about, if you know what I mean.
Yeah, I mean, I try to not ask the exact same things I've asked because that's not really testing your understanding. It might be testing your memorization. Um, but hello. But so I try to ask the idea. So think of how you might ask whether you understand the idea that I've asked in both the homeworks and the quizzes. Some of the questions are very similar. Um, I can't remember now. I wrote that one a while ago. I've been working on your midterm now, but very similar, maybe a little different take on it. So if there's a concept you don't feel like you understand, or you're not sure you understand, or maybe you can bring up a concept and we can try to think of a question that I might ask. We could do that. What concept are you most concerned about? Or maybe none.
Maybe going over, I know for the homework, I think my main issue was my main issues was just the half-life, going over going over
Okay,
how the half-life is affected.
okay.
And I think also the dose rate, but that was just me sort of
You're
um
thinking about
oh
clearance, right? Which we're going to get to.
yeah.
I've tried to do it piece by piece because it gets pretty complicated quickly. So that's why we've waited to do clearance. So we're assuming no changes this week and for the midterm other than what I say. So if there's a change in bioavailability, it doesn't affect anything else. If there's a change in volume, it doesn't affect everything else. You'll learn that may or may not be true depending on the circumstances as we get into clearance. But you don't have to worry about that for this exam or for these questions, okay? It's pretty straightforward. But let's talk about half-life and volume, right?
Mhm.
So half-life is equal to 0.693 volume, which is the topic of the week, over clearance, right? And I want you to think of half-life in the same vein as you think of elimination rate constant because they're just inverses of each other, right? We're correcting for the natural log. So volume also determines K, they're inverses of each other. Yeah, I'll answer that in a minute, okay?
Okay.
So all right, so for this one, so what you could do is put in the volume and distribution equation right into this, right? So we know that VSS is approximated by plasma volume plus tissue volume times the fraction unbound in plasma over the fraction unbound in tissue. Whoopsie. Tissue. Can you see that? I'm kind of at the end of my whiteboard there. I
Yep.
guess I've learned I can pinch this and make it, maybe I can't. Well, I don't know what I'm doing. All right. So if there's a change in any of these things, you're going to see a change in volume, which will then change half-life and K, right? Does that make sense to everybody?
Mhm.
So if I asked you if does a change in volume affect half-life? Yes. Does a change in volume affect K? Yes. Right? If I asked you if a change in tissue binding, how do I get rid of that thing? Change in tissue, oh, something just keeps popping up here. Tissue binding changes half-life. Yes, it will, right? If there's a decrease in fraction unbound, what does that mean? That means it's more highly bound tissues, which means the volume of distribution will go up, which means your half-life will go up and your K will decrease, right?
Mhm.
Does that make sense to everybody?
Yeah.
And if I asked you if it affected your time to steady state, if your half-life goes up, yeah, because we assume about five, clinically we assume about 5 half-lives until we're at steady state. So if your half-life goes up because of a volume change, which was due to the tissue binding change, you're going to see a change in your time to steady state, aren't you?
Hmm.
Or if I asked you if there was a change in K, same thing. You have a decrease in fraction unbound in tissue. It's more highly bound in the tissues now. Therefore, the volume goes up, which causes the K to decrease. The slope is going to get flatter, isn't it? Your peak to trough ratio is going to decrease. Does that make sense? So I could ask you any of these things, right? You should be able to tell me. It's really about understanding this equation and then how it affects these other things, right?
Yeah.
Does that make sense?
Hmm.
You see, it's all building on that first week when we talked about dosing regimen design. We're just digging down into each of these different components. We'll do clearance starting next week, but
And clearance will probably be a little bit more complex, especially
yeah,
the
it's
relationships
trickier.
outlined here.
Yeah. It just adds another level that you have to consider that makes it trickier. Don't worry about that now, just worry about this.
Okay.
Do you guys have any questions? This is a really good question, Gavin. I'm glad I had a chance to go over this because this is kind of the core of what I want you to understand for volume, right? And I want you to know that if tissue binding changes, that doesn't mean plasma protein binding changes. A lot of people think that if tissue binding changes, then nope, they're separate things. They each have their own KD and their own N total. Remember, your bound plasma, your concentration bound, is equal to, let me erase this a little bit, wait, that's a marker, right? I don't want a marker. Is equal to your N total, which is your number of binding sites available, times concentration unbound over your KD plus your concentration unbound. Oops, this is times, right? This is Michaelis-Menten, isn't it? This is the same thing as Vmax, or your capacity of your system. This is the affinity of the system, or which one's more attracted, right, to the tissue or to the protein binding site. KD is the concentration where your half of your binding sites are filled. So this is the same thing as Michaelis-Menten. Capacity and affinity of the system. All right, I had a question kind of along these ways, and why did I don't remember why I brought that up, but I want you to understand that equation too. Hello. Now, how do I pronounce your name? I'm going to guess and I'm going to mess it up. Saida?
Saida.
Saida.
Yes,
Okay, I
ma'am.
pronounced each of those vowels. Okay.
Right.
Saida, hello. All right.
Hi.
When comparing the KD of a drug to fraction unbound, do we use the fraction unbound for plasma? Well, it depends on, and I'm not sure where you're comparing them, but if you have a KD, your concentration bound here is going to be this equation is going to describe maybe your binding to AAG in the plasma. And then there'll be a different one that might describe it to albumin, and a different one that might describe it to binding in the tissue, maybe in your fat muscle, in the adipose tissue. In each of those cases, the N total and the number of binding sites and the KD is going to be for that system. They'll be separate.
Okay.
So the higher the KD, or maybe I'll go the other way, the lower the KD, the higher the attraction. So that's how you look at drug interactions.
Okay.
So like if you have two drugs that are both bound to AAG or both bound to albumin, right? And I give you the relative KDs for those systems. Whichever drug has the lower KD is going to be the one that is preferentially binds to that protein, which means the other one will become unbound because they're
Oh, okay.
competing for resources, aren't they?
Okay.
Does that help?
Yes, ma'am. That cleared it up because I thought I remember you saying it was a competition,
Yeah.
but I didn't know exactly what happened to the one that didn't go through the cell membrane.
Well, I think of it as a love triangle. So whoever is no longer bound is now out, right? So
Okay.
you're no longer bound, which allows you then, I mean, when you're a free drug, you can do things. You can move around, right? You can move out of that compartment. You can move around the body. You can interact with other protein binding sites. You can interact with other uh, with the receptor that causes the pharmacodynamic effect. Because remember, only free drug can actually interact with a receptor. Only free drug is pharmacologically active. If the drug is bound to a protein, it can't do anything else. So it's inert, really.
Okay. I
Does
got you. Thank you.
that make sense to you? Saida.
Yes, ma'am. I'm at
How
work.
you
I'm on
doing?
lunch break.
You're on a lunch break.
Yes, ma'am.
You guys busy? Everybody getting their stuff before a Super Bowl?
We haven't really been too busy because of the Super Bowl.
Oh, good. All right. Does this bring up any other questions for you guys?
No, ma'am.
All right. What other questions can I answer for you?
Is there certain equations that we need to memorize, or are we going to be given the equations?
Well, I gave you, you can look, thank you for bringing that up, Tanya. I put a little, an extra module in your Canvas that has all the equations you're going to be given.
Okay.
So anything that's not there, you need to know.
Yes, ma'am.
Okay.
Okay.
So for example, you need to know, there's probably a better way for me to do this. Sorry. You need to know CSS average. I'm not going to give you that one. I'm not going to give you half-life. I'm not going to give you K. I'm not going to give you CT is equal to C0 e to the negative KT. This is the equation for a one compartment decay model. You have to know this guy. Oh, what else? You need to know S1, F1 dose or dose rate is equal to S2, F2, and dose 2. So if you want to do equivalent, because remember, this is what's going to make it to the systemic circulation, right? And you want to set that equal so that these are the same amounts getting to the systemic circulation. What else? You need to know how to figure out the area of the curve. I do give you the equation for the tail, which is the last point over K, but you need to know how to do that. All your triangles and rectangles. What else? Can't think of anything else off the top of my head, but take a look at what I'm going to give you and that'll help.
Okay. Thank you.
How do we calculate the area under curve again? Is that with the trapezoid method?
Trapezoidal rule, yeah. Do you need me to go over that?
Yes, please.
Okay. All right. So I'm going to just make up some numbers, okay? So let's say we give a dose here. Let's say it's 1,000 milligrams, okay, just for grins. And we're giving an IV bolus because, no, we're not. Sorry, because we want to do one here. So we're going to go from 0. We're going to give it over an hour. Sorry. And let's say our Cmax is 20 milligrams per liter. So this is concentration and this is time. And then say this is at 2 hours. So we'll give it over 2 hours. And then at 6 hours, let's say the concentration is 6. And let's say at 12 hours, this is not to scale, you know, it's 1.5. No, I probably, it's going to be a little off, but that's okay. All right. So what we do is we drop perpendiculars down from each of these points, okay? And we're going to use the rule that we're going to measure actually rectangles here. So this is times 0. So how wide is this rectangle? The width of this rectangle is going to be 2 minus 0, so it's 2, right? The width of this rectangle is 6 minus 2, so it's 4, isn't it? And the width of this one is 6. Doesn't look like it because not to scale, right? So the width is pretty easy to figure out. The height is a little bit trickier. The height is going to be the midpoint between the 2 points here. You try to find the midpoint between these 2 points. So what's the midpoint between 0 and 20?
10.
10. So you just find the average, don't you? So that's 10. So what's the area of this rectangle? 10 times 2 is going to be 20, isn't it? And what's the midpoint between 20 and 6? 20 plus 6 is 26, divided by 2 is 13, isn't it? So this is 13 times 4. What's 13 times 4? 12. Carry the 1, 52. Do you all understand what I'm doing? The tricky part is remembering that you need to find the midpoint between these two. That's what people forget. And then the midpoint between 6 and 1.5, that's 7.5 divided by 2 is what? 3, 6, 15. So that's 7, 5. So it's 3.75. So 3.75 high times 6 hours wide. I'm going to get my calculator out now because 3.75 times 6. Did you guys get 22.5? 6 times 3 is 18. Yeah, that's probably about right, isn't it? So if I just asked you to 12 hours, you're done. You'd add these 3 up, right? So what's 52 plus 20 plus 22.5? 4, 9, right? 94.5. Is everybody good with that? All right, so now this tail part, which is kind of a pain because you got to figure out the K. Remember, the tail part is the last concentration, which in this case is 1.5 divided by K. So how do we determine K? It's just rise over run, isn't it? So I'm going to say, I'm going to do them as far apart as possible. So I'm going to do natural log of 1.5 minus natural log, sorry, my 5s, I must drag my pencil, huh? Minus ln of 20, right? And the difference in time here is 10 hours, isn't it? So natural log of 1.5. Do you understand what I mean by rise over run? So it's a difference in the how much the slope has gone up, right? And in this case go down, which is why it's negative. So K isn't negative, but it's a negative slope on here. So I just want you to make sure you know K is not negative. But the slope is negative, isn't it? Divided by run, so the difference in time here between these 2 points is 10 hours. So it's rise over run, just like what you did in 7th or 8th grade. Which is why sometimes we have to be reminded, because 7th or 8th grade might have been a long time ago. Certainly was for me. So I got for this 0.259. Is that what you guys got? Okay, bye. The recording is going to be right here in the Zoom section on this course, okay?
Bye, guys.
Bye. Have a good day at work. I hope it stays quiet for you.
Thank you.
So we're going to say 1.5 divided by that number, right? And I just keep it in my calculator and keep calculating. So because rounding sometimes, if you round, especially with really small numbers, you're going to be way off. So I got 5.79 for this area. Well, I erased what I had before, so now I have to add them all up again. So 5.79 plus 22.5 plus 52 plus 20 is 100.29. And the units are milligrams per liter, because that's what our concentrations were in, times hours. So milligrams per liter times hours. So if I asked you to round to the nearest tenth, you would say 100.3, right? If I asked you to round to the nearest whole number, it would be 100, wouldn't it? Make sure you can do your rounding, because that can mess you up.
And just to double check, when
Yeah.
we are told to round to the nearest whole number, I mean, if it's like 100.95, for example, or it would be 101.
Yep.
Okay, I wanted to make sure I got confused on that for a problem.
If
It's
I
like
said round to the nearest tens, or 5 or 10 milligram, then you would say 100.
Yeah, I got confused on one problem. I forget what it was. I think it was for one of the quizzes where it's like I rounded down even though it was closer to the units above it because I was thinking, oh, you can't give more than the appropriate dose or something like that, and that was wrong.
Well, Gavin, that's something that I often argue with people about, because sometimes it's more dangerous to be underdosing than to be overdosing. It just depends on the situation. You know what I mean? Some cases you rather err on the side of being aggressive, you know, versus so it's not always that you want to go low. You have to know the circumstance. That's why I just say round it, because you don't know the clinical situation. Does that make sense?
Yep, I understand.
Because I don't believe that's true, that you just always round down. But some people do, so those people usually didn't practice, to be honest. But
Hmm.
it's a little dig, isn't it? I didn't mean
Yep,
that, but
little
it's just
bit.
when you've practiced, you see what you really do,
Yep, that's understandable.
Good?
Yes, ma'am.
Don't be intimidated by this. It's just multiplication, it's not. The one hard thing to do is a K, but you already know how to do a K, so.
I think it just looks scarier
It
than
looks
it is.
scary.
You know?
But to me, actually understanding what to do is a
Yeah.
lot easier than understanding. When you see the equation, it's intimidating, I think.
Yeah.
But it's really just measuring those rectangles. And you all know how to measure the area of a rectangle. What else? Brittany or Kai, do you have anything that is weighing on you?
Um, there was like a quiz question or something where like some of the quiz answers would have like the units at the end. So
Yeah,
then I would like, okay, so I don't put the units, but
right.
there were some that don't, and then I would input the units in there, and then it was like not right, and that was my only
Oh,
like
if that
issue.
that shouldn't be true. If that's
Yeah.
true, let me know, because I don't I mean, I try
Yeah,
to.
it was like like when you read through the question completely, it's like don't put the units
Don't
at
put the
the end.
units in. Yeah.
But then it's like I'm so used to
If
the
you put the
question.
units in, I go back and hand correct it. So the reason I say don't put the units in is because the computer only looks for exactly what the number is. So that's
Yeah.
why I ask you to do that, but I do go in and hand fix it. So if I didn't do that, I just let me know.
Okay. Because like you're so it's like second nature to like put it in, and then
It's
when
very good to put your
I
units
know
in.
that's what like
Yes.
I was always told to do, and so there was
Yes,
like a
and I will
couple.
continue to say that to you. It's just a matter of the computer grading,
Yeah,
you
I'm
know.
just so used to it, and I should have just paid more attention to that. But
I
like, yeah,
apologize if that happened. Good. If I can give you more points, I'm happy.
okay. Um, but yeah, that was the only one, and like the last homework about the half-life stuff and the dose regimen was the same question Kevin asked that
Good.
I
Was that
had.
helpful then going over that?
Yeah, it did. It did
Good.
a lot. It made more sense because like
Good.
it
I mean,
because they're
that,
not
that
all
kind of brings it all together,
related.
right? I mean, that's the whole point of why we're doing all this. So,
Yeah, that helped a lot. But
same thing
those
with
were my
bioavailability, right? Anything that changes bioavailability, right? Bioavailability is decided by FA times FAG times FH, right? Anything that changes any of these is going to change this, which is going to change your CSS average, right?
yeah,
If it's given orally, obviously, if it isn't given by a root, it won't matter. But so if any of these change, it's going to change this, which changes this, right?
yep,
Same thing for gradient of the curve. If it's given orally, excuse me, you change this, you're going to change this, aren't you? And that's the reason I really harp on what determines what. F determines area of the curve. F determines CSS average. Area of the curve does not determine F, right? And CSS average does not determine F. Because a lot of any of these things could change, right? So that's what you have to understand is what determines what. But if one of these change, this is going to change, which is going to change these. It's a cascading effect.
yeah. Because I think I missed like a couple of the Half-Life questions on the last homework. For like 7 and 8, because it made sense in my head that they were like inversely related to like FU and FS, but it turned out it was not the case from
Which
what
one? Which was this in the volume or in the bioavailability?
it was in volume distribution and plasma protein binding
Oh, for
homework
the
problem.
homework or a workshop?
Yeah, it was like number 7 and 8. I thought they were,
Can
I
you
thought
read
it
the
made
question to me,
sense.
Kai? Do you have it in front of you?
Yeah, it was like if your patient is taking a drug that's highly bound to AAG, what would you expect to happen if your patient underwent surgery? And it would be like part A would be like what would happen to FU for this drug? What would how would this affect VSS, and how would this affect
All
T1
right,
heavy?
I think I know what you mean. So there's an increase in AAG due to the surgery, okay? There's
Yep.
this acute phase reactant that gets thrown out. So if the drug is a substrate of AAG, what's going to happen to the fraction unbound of that drug?
Uh, it would decrease.
Right. Does everybody see that? Why? Because it's more highly bound. So the fraction bound increases, therefore the fraction unbound is going to decrease. It's more highly bound, right? So your
Yes.
fraction unbound decreases, right?
Yes.
And so then what's that going to do to volume?
I put decrease as well because I
And you
thought they
were
were directly
correct. Yep.
related. Yeah.
I'm lazy about putting these P's in here, but so if that decreases, the volume's going to decrease. It's more stuck in that small compartment, right, of the plasma.
Yes.
So the volume of distribution decreases. So then what happens, let's say to K? What happens to K? That
It
wasn't on
wouldn't.
the homework, but I could have asked you it, right?
Oh, oh, that's what I was like. I was checking. Is
It's
high enough.
asking the same idea, isn't it? What's going to happen to K?
K would go down. No, if
Look at that equation there. Can you see it?
no, K would go up because the binding affinity is decrease.
No, the binding is increased, right, in the plasma. So since the binding is
Oh,
increased,
in the plasma, yeah.
it's more stuck in that small compartment, so the volume goes down, which means the drug is more available to those clearance organs. So what happens to the slope of your line? It gets steeper, doesn't it?
Yeah.
So the K increases, doesn't it?
Yes.
The rate of elimination goes up.
Because they're
And
more
then what
tightly
happens
packed.
to half-life?
I put increase, but um, but
If
maybe.
it's more bound and the volume goes down,
Yeah, I think you're right. I didn't even factor that. I thought it was like inversely correlated to um
half-life.
yeah.
Well, you need to know this equation and this equation, but I also kind of want you to understand it. So if the if the drug becomes more highly bound now because there's more AAG in that small plasma compartment. Remember, this is not a good picture of a person, but let's say this is your total body water. And for a 30 or 70 kilogram person, there's about 3 liters in the plasma. This is the plasma compartment. And in comparison to 39 liters of tissue. So this is a much bigger compartment, yeah, 10 times, more than 10 times, right?
Yeah.
So if the drug becomes more, and remember, the only way a drug can move between these two is if it's unbound.
Okay.
So if the drug becomes more highly bound in this little itty bitty in the plasma where the AAG is, in that little itty bitty becomes more bound there, it can't move out here. So relatively, the volume distribution gets smaller, which you can see with this equation. But I kind of want you to understand it too.
Yeah, I'm trying to make that
It depends on where it's more highly bound. So now it's more highly bound in the plasma in that tiny compartment. If it were the opposite, if there's not AAG in the tissues, but let's say a drug becomes more highly bound in the tissues. If that happened instead, so instead of this, it happened in the tissues, became more highly bound, which means a fraction unbound. Now our volume's going to get bigger, isn't it? Because
yes.
it's
Okay.
bound in this big compartment now and stuck in this big compartment. It can't go back in here as easily.
Yeah, that makes sense.
And
Yeah,
then the opposite happens here, right, Kai?
yeah, I think I still am like slightly
Still learning
um,
these concepts?
yeah, the whole like unbound plasma versus unbound tissues sometimes get swapped.
Right. Now you got to think of them, like I said, as two separate systems.
But now it makes more sense.
It,
Yeah.
just so like you can't, they don't, like the fraction unbounds don't add up to one. It's like if you can have 95% unbound in the plasma and 95% unbound in the tissues, or you can have 86%. You've seen problems like this, right? 86% bound here and 20% bound here, right? They're not, they're separate animals.
Okay.
But the really important thing you need to understand is, so if the volume in this case goes up, right? Now it's spread out more, so it's going to take longer for the drug to move back into the plasma, which is where it has to be to get the clearance organs of the liver and the kidneys. It's just going to take longer. So what's going to happen to your elimination rate? It's going to get slower, isn't it?
Yes.
And what's going to happen to your peak to trough ratio? It's going to go from this to this. It's going to get smaller. And what's going to happen to your half-life if your volume gets bigger, the opposite of what this is? If it gets bigger, your
It gets
half-life is going to
bigger
get
too.
longer, which you could have told me, right? Because if it's taking longer to get rid of it, that means there's an increase in half-life. Okay?
Yep, that makes more sense. Thank you.
Good. Thank you for asking it, because if it helped others, that's very important. It's an important concept. Let's see, Bridget and Day, is that how I say your name?
Yes.
And Bridget and Day are joining us. Welcome, welcome. You guys have any
Thank you.
questions? Anything that's worrying you or got you stumped?
Mm, Not yet. Think I'm just
Good.
reviewing with you guys.
Good. I hope you were able to see. I posted a quiz review of the dynamics and bioavailability quizzes. So make sure to take a look at those if you have any questions. There's also a video of the dosing regimen design quiz, and I'll be posting the volume quiz hopefully by about noon tomorrow for you. Okay. Also, I think I told you in that module, I added that module that has the equations. I also have some practice problems in there that you can try if you want to practice. And I told you the ones that apply to you because that's got questions from the whole semester, and we haven't covered the whole semester yet since it's only week 4. But we've covered a lot, so you should be proud of how much you've learned. But I told you the questions that you should be able to answer.
From a purely test admin perspective, because I know someone's gonna ask or forget to or will want to know anyway, but like, do we
Yeah.
know how many questions you're putting on the midterm?
Well,
and
right
how
now
many,
I've
how
got
much
50
time?
on there. That's what I've always asked in the past.
Okay.
50?
And a lot of them will be very similar to what you've already seen, so you should be able to move quickly on those, you know. It's others you're gonna have to stop and think about more. I thought about decreasing it, but then that gives more points. You know what I mean? It's always a balance, you know.
Well, wait, hold on.
So
You say 50 questions?
yeah,
That's a
50
lot.
questions and how long?
an hour and a half,
Okay.
Oh.
It's too,
90 minutes.
I know,
probably
I know somebody's gonna want to know
It's
the
a tiny bit less than 2 minutes a question.
There
about 2
was
minutes a question.
another
No.
question I think we talked about, I don't know, but when would we need to adjust like a change in the in initial loading dose if like a patient has like hem like
Don't worry about it. We're gonna go over that later in the semester.
okay, because there was like something about that with like half-life and a patient with like reduced clearance or something, and I thought that was
It
like
won't
kind
affect loading dose, but don't worry about that right now.
of okay.
We did talk about how VC, I guess maybe you should know, VC is used to determine a loading dose. That's your central compartment where the drug distributes to initially, which is really
Okay.
just the volume of your plasma and your highly perfused organs.
Okay.
But don't worry about, we'll be talking about that after Dr. Basu does his stuff, then I'll come back and talk about dosing then.
Because I thought something about that with like the half-life, like it says like, you know, if the half-life changed and you had to like come up with a dose regimen, if it was something like related to that to bypass the
Well,
toxicity or something. And but I
if the
guess
half-life changes,
yeah,
you probably do need to make a change in your dose interval, right? Getting
yeah,
back to the dosage regimen design stuff. But that's what I'm going to expect you to be able to talk about.
okay. That makes more sense. Because I was thinking like maybe like to get around it, we just give them more at the start and then like a smaller maintenance dose to bypass the whole like
Well, sometimes
half-life.
depending upon, you only really give a loading dose if there's an emergent situation or if it's just going to take too long to get into the therapeutic range. So if you ever like there's a drug called amiodarone that it has a half-life of 30 days.
Oh,
So it's going to be, 5 months until they're at steady state, right? So you don't want to wait 5 months until you get the drug where you want it to be. So you give kind of a loading dose with that. Does that make
okay.
sense?
So we won't have to do that on the exam. It was just more.
No, that's not till the final exam. Don't
Okay.
worry.
Oh.
Worry about that one later. And hopefully I'll have taught you something about it by then too.
um. So 50 questions, I think you said.
Yeah.
Um.
And you've got your equations. It's going to be on ExamSoft. You can use your whiteboards and your calculator. Just got to show them, you know, at the beginning and at the end, along with your workspace. What else?
Do you know the breakdown of the 50 questions? Like, are they going to be a
I
lot of?
tried to make it very even. I think I tried to make it 12 to 13 questions on all 4 topics. The 4 topics are dosing regimen design, pharmacodynamics, bioavailability and bioequivalence, that's considered one topic, and then volumes and distribution, protein binding. So that's the 4 topics.
And what do you recommend we used for practice? Just going over the
There's
homework
some
again?
practice problems in there, and go over any, you know, go over the quiz. You've got the quiz questions because I've given you to you through the videos, and also look at your homework and workshop. Those should all give you practice, and try not looking at the answer and see how you do and see where the breakdown is then, you know.
Okay.
And then there's more questions. So there's more questions in those practice problems in the module. But there's only answers for the odd ones, I think. So good? You feeling strong? Pharmacokinetic strong. All right, you know, you can always text me or you can't text me, I guess, but email me if you need something, if you have a question. I think Andy's probably going to have his tutoring on Monday night still too. I'm going to be doing a review session like this with the on-campus people. I'm going to, if it's okay with you guys, I'm going to post this for them, and I'll post theirs for you, so that you can see what they asked, if there's any additional things that maybe they thought to ask that you hadn't. How does that sound?
That sounds great.
That
Is
sounds
that
good.
okay with y'all?
Yeah,
Huh?
that'd be great.
Yes.
So that's at 3 tomorrow, I think, so I'll try to get that posted as soon as that's over on Monday. I'm excited to see you. Show me how much you know. You're going to do great, but you got to study. These ideas are not intuitive, I don't think. So some of them are, but most of them aren't. All right, then I'm going to let you go. I hope your team wins if you're going to watch the football game.
Thank you.
Thank you for coming, guys. Thanks for working so hard. Let me know what you need, okay?
Okay, thank you.
Thank you.
Bye-bye.
Bye.